Another draft physics video presentation. Sort of in draft mode on this one, kind of doing this before it's really cooked or ready. Just some discussion about spectral lines, structure of an atom, the basic mechanisms that have to be involved, or what we can, some of the conclusions you can draw. Some, at least, speculation regarding conclusions. I don't know. Whatever. Ideas. Theories. Potential possible ideas relevant to the subject of photons. The conversion of energy between the force bits and the electron bits that seem to be doing most of the interacting. The protons probably are involved, but they are in such a subtle way that you don't see it, in an end result. You can sort of understand that about an atom and these different ways of transmitting energy through the whole atom. So you have the whole atom that has the protons and the electrons. You could just draw it like that, I suppose. And these energy goes in. Yeah, you can almost see that. And then lots of different things can happen, right? The energy can go out somewhere else. It can go out, it can be transmitted, and that way something is transparent. That is, what comes in comes back out, or else it gets what's called absorbed. And then we know absorption is connected to heat, so it's still there if it's absorbed, and it'll end up getting radiated. I could use squiggly lines, I suppose, in some generic, who knows what direction. And then you have the idea of a reflection. So you have transmission, where it gets through the thing and stays intact. You have absorption, which means it can be converted into something else. Larger frequencies and all kinds of other stuff can come out. And then you have the idea of it reflecting. So more than one thing happening, kind of hard to consolidate that into a simple story. Alright, so as I pointed out, I guess the first thing to agree upon is that we know the polarization of light is pretty large, 2,000 atoms worth of polarization. And so whatever this thing is, you want to believe it's a little wave or whatever, that's fine, but you do have to kind of acknowledge that one electron is a tiny location to be affecting by something that's so large. And so this idea of one photon hitting one photon hitting one electron, just this one, and it doesn't bother this one or this one or this one or any of the other ones, just doesn't have any practicality to it. It doesn't make much sense. The energy can't do that realistically. It just doesn't make any sense. So you have to think of this thing more as a composite effect, that it's affecting more than one photon is affecting an electron. So you could think that, if you understood that it has a polarization and that you could line a bunch of these things on top of each other, they'd all be in the same area. So it would essentially be a bunch of little bits, and then a bunch of little bits in an empty space, and a bunch of little bits in an empty space, and that this stuff doesn't really come in single quantities, and so that you can hit the same electron with different photons, essentially. You could hit it with a piece from one photon and then another piece from another photon, and with these arrangements, these, however you want to, like I said, you have them all lined up in the same phase, but they're in different locations, and where they're out of alignment is in different places. So one of them has a peak here, and one of them has a peak here, and those two are on the same line, so those two have the chance of hitting the same electron. And we know the electrons don't move terribly straight either, so you can kind of see if you hit an electron with a little bit and the electron moves here, well, then maybe the other piece at the right frequency shows up from the other photon and then hits it again and moves it here. So you can kind of get the idea that it's an additive thing, that the idea is one electron, the phase is going to say, okay, it hasn't rebounded, So that's the other part, right? We know. Okay. Yeah, we know. So we're going to get into the atom structure, but the idea would be is that the atom has the nucleus thing in the middle. That's positively charged. The electrons are negatively charged, and that they arrange around the charged nucleus through attraction and then their mutual repulsion this way. So they're attracted to the thing in the middle, they're repelled by each other, and there's a balance in that tension, I would argue. I think I can say that pretty confidently, that that's what defines the shape of the atom. And one could intuit, just because of the inverse square law, this pressure, is greater on the inside, because you have to, you're opposing a stronger force. The force gets weaker and weaker as you get further away. Well, it's not really the inverse square law, it's the R law. So the force gets twice as weak, twice the distance, that kind of thing. So obviously, you could sort of understand that these electrons, if you were to vibrate them, they would vibrate at a higher frequency. They would bounce. If I put a pressure in here, the pressure will be spread among the electrons and they'll jiggle. Okay, and so I can understand that the ones that are out here, the ones that get placed in this secondary orbit where they're still repelled by each other, but they're still attracted to the proton, that they would jiggle at a much higher, much longer, they're slower, because there's less tension and there's more distance between the electrons to transmit any kind of irregularity, and so the tension will be less tension, and that's really all they have is tension, which is a kind of potential energy, not a real energy. It's just circumstantial to where they are. All right, so so I guess I could say the idea of a single photon emitter is not going to work. I don't think the two-slit experiment, as I demonstrated, could function if photons could be sent as individual photons. If there was such a thing as an individual photon sender, that you wouldn't get the pattern accumulating by individual photons, that you really need to have more than those pieces together. But anyway, so I would argue that if you think about how photons are created, then you can get some idea, and on how they're received is what we're really talking about, in a way. I mean, what's defining what a photon is the receiver, the thing that says it's a photon, more than the thing that sends it. What it sends, who knows? We know what it has to be received as a photon. So anyway, I have speculated that it's not much different than the antenna idea, and that the deciding factor is how the speed of light is the limiting factor, and you can only get up an antenna at a certain speed. And as you're going up the antenna, you're creating the bits of the photon, and its polarization is essentially the limit of the antenna. So for very long wavelengths, wavelengths that would be this kind of polarization, you're kind of just saying any antenna will do. I mean, the longer I can go, the better, because I can still use all that because I have plenty of time. There's plenty of time between the cycles, so I have lots of time to get up the antenna and create a little bit of energy that's going to wiggle off of the antenna. But for the higher frequencies, you're kind of out of luck once you've gone, like for 3 centimeters would be something like 10 gigahertz. So at 10 gigahertz, you go longer than 3 centimeters, your antenna can't really do anything constructive, because by the time you got up there, you're too late to send a bit out, because it won't be at the right frequency. So the only place that is effective is in this short distance, and the truth is light is a very high frequency. So I don't know what it is in gigahertz, but it's a lot of gigahertz, and so its antenna is essentially just a row of atoms. So there'll be a row of atoms in a substance, and all you're really doing is shoving a voltage at these row of atoms. So the idea, you can see that, right? Yeah, good enough anyway. So the idea is you're going to send electricity in. And so the electricity is in the form of an electron, essentially, that's moving. Right? And its voltage is the speed, its momentum. So voltage equals momentum of the electron. So the faster it's moving, the higher the voltage. And the more of them, okay, the more of the electrons you have moving, the more atoms you're going to affect. That's amperage. So amperage is the number of electrons, and voltage is the pressure, that is the speed of the electrons. And so, yeah, so amps equals volume. Yeah, that won't work, right? So yeah, okay. Well, you can't read it anyway, so it doesn't really matter. All right. So, and the idea is that the electron at a certain speed hits the atom, and it's going to take a certain, and that atom will eject a photon, a piece, a bit. It won't be a photon yet. It's just a bit. And then it moves to the next atom, the pressure, and it's going to do the same thing in the sense it's going to release a little piece of force. Now, the release of the force is really just a reflection. So if you can understand that the universe is constantly shooting energy at things. Sorry. Stop it. Wire. Stop it. Crappy connection, whatever you are. Alright, so the universe is sending energy at things. And so if I move the thing, you can sort of understand the more important movement is away. So if I move an electron away from this force, then this force can't hit it and reflect off of it. So an eyeball looking this way, looking at what's happening, is not going to see any reflecting because this thing is moving the same way as this stuff, so nothing can reflect. And so it's not until this thing stops or moves in this direction that I will see, okay, the reflecting bits. So nothing reflects if it's moving in the same direction as the force, or less reflects, you can understand, depending on its speed. And so what you're really just doing is moving electrons to create gaps, and places where there's stuff reflecting, and then when the electrons move right, there's nothing reflecting, and then there's stuff reflecting again, and then there's nothing, and then there's stuff reflecting, and that's a photon. So you have to do that going back and forth thing a few times to be able to create enough little bits, for us to see it as a photon. That would be the idea or the rule. So anyway, but that you don't have to really understand all of that to understand. I don't know if I need to erase it yet. Anyway, all right, so back to this. So obviously, as this electron hits this electron, that is, it pressurizes it. It moves towards it, which means it's going to create energy back and forth between the two. It's going to create pressure. That's going to move this electron. That electron's going to put pressure on this electron of this atom, and this electron of this atom, and the electron of this atom. And as they keep doing that, they keep pushing the electrons this way, which means this world that's shooting energy down is going to see essentially the atoms change from that shape to this shape. And when they change from that shape to this shape, these electrons are pushed out, which means they're telling the universe, reflect off me sooner. So it's really just about moving electrons this way by pushing electrons this way. And you can sort of understand that. If I push on this electron, you could understand that these two electrons will go this way because of the extra pressure. So you can sort of understand that, that's going to be the change in the universe, is that this pressure is going to create more pressure and expand some other electron in this direction. So it's changing essentially the dimension of the movement. All right, so anyway, so the electron moves, hits this electron, that electron pushes this electron up, which creates this opportunity for this, and the same thing happens here, and then it happens here, and then it happens here, and it happens here, and so they're all happening in a sequence. So obviously this one gets way ahead of these because they happen later in time. So you end up with a bit here, and a bit here, and a bit here, and a bit here, and that ends up being your photon. And that's why the polarization is connected to the wavelength. That's what's connecting the two. That's what's making the two proportional to each other. The wavelength is the speed, and the well, I mean, it's the speed either way you look at it, but just pointing out why the spread, it moves across the atoms, and as it moves across the atoms, it's creating the frequency and the polarization. I think that's understandable. All right. So now, what parts of this are essential to, some background before you get into, trying to explain how energy passes through, say, a gas. So this gets into like spectrometry and stuff, where where you take the atoms and then shoot a bunch of light through them, and you see which ones are absorbed and which ones are emitted. So this is about sort of absorption lines and emission lines, and why there are specific lines that kind of tell you what the atom is, because there's a certain arrangement of its electrons in a certain way the pressure is dealt with by the atoms. Alright, so we'll play some of this. I mean, the real point is this is another one of those plus and minus things, okay? Like the conventional model, as I understood it, okay, of the atom was that, okay, yeah, you have the nucleus, and then you have these electrons in what are called shells, okay? So they're at a distance from each other. But I would argue that the wrong-headedness of this was to think of it as solar systems, or to think of it as a gravitational model, when it's really a charge model. It's really magnetism, I guess. The way to think about it, I would argue, is to think of it like a little magnets. And if you could create a south magnet, okay, just a south pole, and that's what a positive charge would be, as a south monopole, and then you had north monopoles. It's sort of like thinking about magnets in between two pieces of glass. So if I put magnets in between, little flat magnets between two pieces of glass, and I put them the same side up, all the little ones, and I had a big one in the middle that was, the other side, flipped the other way, you could sort of understand that I could position the magnets where the north magnets will be repelling each other. You see, yeah, you can see that enough. And the and the south magnet would be attracting, and that there would be this tension between these, in the sense that this one can't get closer to this without getting closer to this. And so for every pull there would be this way, there's a pull resisting that pull. And so you could understand that I could actually position them in the glass where, if I was careful about it, they can't flip, so they can't change their magnetism, that they would sit in these positions, and then I could poke on this one, and I could make these all move a little bit. So I could jiggle the whole section of magnets by just jiggling one of the magnets. And so that's the tension, I think, that's really holding atoms together. And the whole notion that electrons are affected by gravity, as I said in the other video, is probably just wrong, in the sense that gravity, all they know is the charge. So all they know is they're getting hit by these two kinds of force, the proton and the electron force, the one that they reflect and the one that causes the right turn. So don't know how to, there's no, without getting way too complicated, there's no way to go into all that crap. But the point is that that's the there is gravity, but it's not technically gravity to an electron, because the electron is seeing it as proton and electron force, and depending on which force it's seeing. See, the reason why the proton is attractive is because all of the N force, okay, goes out of the proton in a new dimension, and all of the N force that goes anywhere near the electron, it goes into the electron, ends up leaving it, and the S force, the opposite forces. So there's nothing, this ends up being a vacuum of force. That means there's a lack of energy, a lack of little bits between in here. This space gets evacuated of little bits, and no little bits can get in this way because any n bit that hits here reflects, and any s bit that hits here leaves perpendicularly, so nothing can technically get in there. And if it comes in this way, it had a potential to get in here, but the fact is that if it's moving, it ends up sending it in the opposite direction of its movement, so it always ends up going away, so it doesn't go in. And if it's not moving, then it can send one this way now and then, and that's enough pressure to keep it from ever getting too close. It can't get really, really close because enough energy leaks in between them, so there is a minimum that keeps a minimum distance, but that doesn't happen until they get fairly close, so there's no point in discussing that. So anyway, see, that's the part that'll just, you know, if you haven't been following along, that's probably, you're like, what the hell? But anyway, I don't care. Yeah, this isn't for first timers. Alright, so I'm just saying that their model of these things zooming around, you know, because they have to have some reason for them not to be falling into the sun, right? You can even use that analogy, because they made a gravitational model. They don't need to be moving if they're magnets, is my only point. So they don't have to be swirling anywhere or doing any of that stuff, and it just makes the whole idea of a shared, like say two atoms that connect each other, when they have a shared electron, I would argue it's obviously just shared in a real sense. Okay, like, you know, I can make another atom over here, right? Another S, and you could understand that it could have its other electrons, and it would be literally sharing this electron. You know, they would actually share its position. It would stay in this position. This would stay in these positions. That these things have real shape. And, you know, the swirling thing, I don't think works at all in terms of being able to consistently hit something. Where does the energy come from? Where does it go? You can ask so many questions. How does it get into the orbits? Because you really can't get into an orbit from the outside unless you hit something, you know, to slow you down. So, you know, there's lots of things that just doesn't work as a gravitational model. All right, so it's I would argue a magnetic model, that it's magnetism holding, a kind of magnetism is holding the atom together. And clearly the stuff on the inside is high pressure. So that's consistent with what we know about, like, the Earth or something. And high pressure just means higher tension. You know, it's more rigid in its position, and it moves less distance. If you hit it, it's the opposition to the movement is stronger, and it stops the jiggle quicker, and so it'll jiggle like something under higher tension. That means it will only jiggle at higher frequencies than the stuff out here that just lazily can jiggle. This stuff jiggles very high, very fast. So that is why you could argue the inside of an atom is the place where you have to create movement inside these tight orbits, the inside orbits, to make something like an X-ray. These are the electrons that'll jiggle and create pieces of a photon and piece of a photon, piece of a photon at the high frequency. Okay, so you need to jiggle these inside electrons to make an X-ray, and that's why X-rays are hard to make. It's because it's hard to get energy in the inside orbits, because all these outside orbits are likely to degrade the photons before they even get to jiggle the inside fellows. It's hard to get to them. So that's a simple enough answer. Alright, so yeah, now we'll play some of the video and such.
Here's a very simplified model of an atom. The nucleus at the center of the atom is where the protons and neutrons live. But they're kinda boring because for the most part they just sit there. The real star of the show is the electron. The electron gets to do all the interesting stuff like move around, jump around, bind with other atoms. These dashed lines represent...
So that's sort of true. Like I said, I would agree with that. And frankly, the photons, I think, are just made out of the energy that electrons are sensitive to. So it's electron force. the basic function of photons is to move electrons.
Represent the different energy levels the electron can have while in the atom. We like representing these energy levels with an energy level diagram. The energy level diagram gives us a way to show what energy.
So they're using this terminology. So this is another thing So anyway, so their original model basically says the inside is 0 and the outside is 7. And then later in the video he points out how, well, really you have to put negative numbers in front of these things, and so they're going to convert the 0 into 10 and then make the outside that's now 7 into 2 or 3 or something, whatever, 10 minus 7. So they just completely invert it. So you're saying, well, which is it? Why don't you just stick with one thing? And so they're using electron volts, which isn't a very good way of describing the tension. I mean, it's all potential energy. There's no kinetic energy that it's expressing, so it doesn't have any energy on its own. And all you're really saying is how much energy does it take to knock it out of that tension. So you're just saying the pressure is it wants to stay where it is. So it has a higher stay where it is pressure, and so it takes more energy to get it out of there. That is, you have to hit it quicker with something because it bounces back really quick. So if you're gonna try to tip it over, it's the kind of thing where the pendulum moves really fast. So you got to hit it with energy, and then you got to hit it energy again while it's over there. And so you have to do that very quickly because it rebounds very quickly. And so only an X-ray or something that hits it with a frequency very often is going to get it out of there. Yeah, that'll probably do.
The electron has without having to draw an atom with a bunch of circles all the time. Let's say our pretend atom has electron energy levels of 0 eV, 4 eV, 6 eV, and 7 eV. Note that moving left or right on an energy level diagram doesn't actually...
Yeah, well, that's not even needed to say. So again, that's the traditional notion that the weak energy level is the one in the middle, the one closest to the nucleus, which just doesn't make any intuitive sense. It's obviously the one under the highest tension. It has the highest potential in the form of resistance to motion. It's bound by two powerful forces fighting each other. The force of the electrons against each other is stronger in that orbit, and the attraction to the proton is stronger. So the two forces are fighting each other in a stronger way. The elastic is tighter there than out here.
Represent anything meaningful. So technically there is no x-axis on an energy level diagram, but we draw it there anyway because it makes it look nice. All that matters is what energy level or rung on the ladder the electron is at. Note that the electron for our hypothetical atom here can only exist with 0 eV, 4, 6, or 7 eV. The electron just cannot exist between energy levels. It's always got to be right on one of the energy levels.
Right, well that's just sensible, like I said, based on the configuration of these as magnets. You could understand that if I was going to add another magnet, it has to be here. It has to balance its forces with the other two electrons and balance its attraction to the proton, so there's going to be a specific place it can only be based on its distance relative to the things it's attracted to and the thing it's repelling against. So obviously there would be standard locations that would be the only permittable location, because the magnet won't stay here. Okay, it can't stay here because the pressure is too high with that electron, so it can't stay there. It can be there, but it won't stay there. See, they're saying like it can't even travel through these other things. Well, of course it can, but it won't stay there.
Okay, so let's say our electron starts off on the 0 eV energy level. It's good to note that the lowest energy level an electron can have in an atom is called the ground state. So how could our electron get from the ground state to any of the higher energy?
Right, so that's just to me really bad terminology, because we kind of know the ground state is the external state. The state where the electron is unmotivated, essentially.
levels. Well, for the electron to get to a higher energy level, we've got to give the electron more energy. And we know how to give an electron more energy. You just shoot light at it. If a photon of the right energy can strike an electron, the electron will absorb all the photon's energy and jump to a higher energy.
Okay, so that's the kind of thing where they say something that's just too simplistic. Like I said, we know that the photon is 2,000 times the size of this. All right, I mean, its polarization is, it's spread. The area it's spread over, whatever you want to call that wave, you know, that thing, you know, again, I'm conceding that you're totally incapable of understanding a particle theory, you know, and so even if you make it a wave, even if we concede this notion of a wave, you have to understand that you understand the wave is gigantic compared to the size of not a specific electron, but even by the size of the atoms. It's spreading over 2,000 of them. How can it hit this with all this wiggling? It can't do that. So I mean, this simplification is way too simple, and it really just doesn't get to the, you know, the idea is that what you're doing. See, the thing to understand is the higher the frequency, this is proportional. You can see that, yeah. So if I go with a lower frequency, the polarization is wider, so the spread is wider. So the higher the frequency, the more likely I am to hit at least related elements. I'm more likely to hit this and this one with the same photon or something like that. So the more it condenses, the more likely it is to hit at least related electrons. Or in the case of, like I said, most metals are crystals, so you have to sort of understand that there's a bunch of electron atoms that are behaving as one object in some sense. They're tied to each other, so if you can hit them with the energy across that whole crystal, then the whole crystal can vibrate essentially, and send the signal to the other side, okay, and create the effect of transmitting or, you know, preserving the profile of the energy that went in. The energy went in will come out the same way because the crystal will preserve it. Certainly with a phase, possibly a phase change. Obviously it takes time to blend the effects and then send them to another atom. It takes time for it to move electrons to different locations because it's not moving them in straight lines. It's often pushing these out to push this one out, you know. It pushes these out, these push back in, that pushes this one up. So, you know, the energy goes in this way and it comes out that way, but it only comes out that way by doing this and then this. You know, now you can't see that, this and then this. You know, it's first pushes it out and then that swings back in because it's related to the proton. When it swings back in, it pushes against this one. So it's moving, it's changing the center of the gravity in a sense. When it pushes this one out, it pushes it up to this location. It comes back to this location, which is too close to this location, which pushes this one to this location. So the whole thing is moving. This whole orbit is essentially getting moved from there to, you know, there, and then this probably moves to compensate for that, but whatever. The whole point is you start jiggling atoms versus just jiggling electrons, and that, what I would argue, is when you're transmitting. That's when you're being transparent, is when you actually make the whole atom move in the direction of the momentum. So if you can get the whole atom to move, then so if the whole atom moves, you know, from here to here, then you're going to send it to the next atom, to the next atom, to the next atom. So if you get the atom to move, you'll transmit. If all you're moving is one electron, you won't. Or if all you end up doing is pushing this part out, but it never pushes out that way, and this one just ends up going back here because you didn't keep adding pressure. So that's where it gets, you know, There's just a lot of physical dynamics. There's a lot of ways energy can affect this system. I don't know if there's a lot. There might be 5, but it's just, detailing them all, it gets a little complicated and which ones are more likely. My simple argument is that this idea that a single photon hits one electron and bang, hits it and then hits it and then hits it and then hits it is unrealistic. And what really has to happen is pieces of different photons have to hit the same electron to absorb that energy or to break. So each time the photon, so let's say I drew a photon more realistic to how I think they look. Okay, so now I haven't made this polarization anything as wide as it really is. So it's really, hundreds of times bigger than that. But the point would be as these little bits are coming in, and obviously you can see that, this would only take out one bit of this photon. I should line that up better. So this bit will hit the electron. The rest of the bits will keep going. Okay, and they might hit some other electron in another atom. And so with each interaction a bit of a photon has with an electron, it's losing a piece of itself. It's breaking. And what's really going to happen is after you go through all this stuff of going through these atoms and hitting electrons and moving them to new positions, is you're creating reflections, and the reflections are going to take the place of the original bits. The original bit goes in, moves the electron, and now a new bit comes out in terms of a reflection from the field. So the position change will create another piece of energy, so to speak, a new a place where there's gaps. Again, I don't know how to say this gap part again, but the real important feature between the thing that makes photons distinctive, the thing that gives them their energy, isn't the photon bit, isn't this bit, it's this separation between them. The field doesn't do separation very much, right? So maybe that's another thing to understand. So this is just another one of these little subtle facts that are probably really important, and I just haven't gotten it all together enough to really explain why it would be important, but you can sort of understand. So if I had a dense field of little bits moving in all kinds of directions, so I'm giving them a geometry just because it's easier to draw, so they have a certain tightness. What you're really doing when you make a photon isn't that you're adding bits, it's that you're subtracting space. So what makes this one distinctive is the fact that it has all this empty next to it. That is no pressure. So when you're hitting something with a photon, in a way what you're hitting it with is an opposite force, where you're taking away what usually is there. Usually there's this much energy hitting me all the time. 3 things are always hitting me. 3 things are always hitting me. If a photon shows up, then all of a sudden it's less than 3 things hitting me. Only 2 things hit me. In a sense, I'm going to move towards the photon. In a sense, it's less pressure. So the photon is really sort of an anti-pressure in some sense. It's taking pressure out of the field. And when it's doing it at a high frequency, that means it's taking a lot out of the field. So you could sort of understand that a high frequency photon has, even though they're closer together, even though this frequency is closer together, the idea is that when you add up all this space, because there's a lot of it, I don't know how to, that doesn't sound intuitively correct, so I don't want to jump onto the boat too soon. But the point is the space is what's really defining the photon. The field, the electrons are constantly getting hit by stuff. Okay, so they're constantly being hit by stuff, and what makes the stuff of a photon interesting is the fact that it's not just stuff, it's stuff with gaps. And the gaps are what's really creating the fact that it can rebound. So the energy hits it, but there's a gap right after it, a lack of energy. So it has to obligate the object to fall backwards because there's an absence of stuff right after it. There's not a presence of stuff, kind of thing. So it, in a way, provides the opportunity for rebound. Yeah, well, as stated, draft. I know it's critical, and like I said, that's why I didn't want to mention it, just because I knew I'm not going to say it right, though. But I'm thinking that's going to be a truth that underlies this, is that the real power of the photon isn't so much that it has the quanta, it's that it has the absence of quanta at a regular frequency. It's the empty spaces at the regular frequency that are really creating the opportunity for something different to happen. All right. So we'll go back to the video. I believe so.
Level. The electron in this ground state needs 4 eV to jump to the next energy level. That means if a photon that had an energy of 4 eV came in and struck the electron would absorb the energy of the photon, causing the photon to disappear, and that electron would jump up to the next energy level. We call the first energy level after the ground.
So I would argue that it just means how many little bits are going to have to hit it. See, all the bits have the same power, the same momentum. The bits inside of an X-ray and the bits inside of a infrared have exactly the same potential as little bits. And the only thing that makes them different is how the time between them. And the time is the tipping point thing. Time means it doesn't have time. The faster I hit it, it doesn't have time to tip back. It can't get back to its original position. And that's what makes X-rays more powerful, is they can hit something and hit something and hit something before it's had time to reflect or rebound. And the key would be is that it would take at least like 4 photons worth of X-rays to be able to hit the same electron. 10, 20, a million, whatever the number would be, but it's more than one X-ray photon has to travel that path for you to have any hope of hitting the same electron enough times to give it enough momentum to leave. And that's really the key here. So we're just talking about when did you create enough movement in the electron to get it to leave, to get to the zero state. As it's leaving, it's absorbing energy because it's fighting the pressure of the proton attracting it, so to speak. So you can think of it like pushing your way out of gravity. Well, when you push your way out of gravity, it doesn't mean that you have a whole bunch of momentum to keep going. You could have used all your fuel just to get to the point where the Earth is pulling on you so weakly that you only need like 1 mile an hour to keep to not fall back in. So there's a point where you get to a point where the force is so weak that you don't need any energy to go any further. And that's sort of the state. You're just trying to get the electron, you push it out, but when you push it out, it's not like it's going 1,000,000 miles an hour. It doesn't have any energy. It's run out. You used it all up to push it out of the gravity, so to speak, out of the attractive pressure.
Ground state, the first excited state. Once the electron's at the higher energy level, it won't stay there long. Electrons, if given the chance, will fall towards the lowest energy level they can. So our electron will fall back down to the ground state and give up 4 eV of energy.
So it really won't if that ground state is full. So if you already have, they say something like that, but it doesn't really make any sense, right? I mean, come on. So I have a proton, and I have magnets in all these positions, right? Well, once the position, let's put one here and one inside the board just to understand, it's 3-dimensional. But I'm sort of full, right? So with 6, I'm full, and it just depends on how I arrange them. I could arrange them hexagonally, and then I could add a few more, right? So I could put them here, 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 and here. And so then I could have 5 plus 2 or 7. 5 plus 3, right? Yeah. So I could have 8. So depending on where what geometry I use, I can put more in by just changing the geometry of their proportional relationship to each other. So each electron that's in a specific orbit or geometry has the same pressure, and the ones that would be in this geometry obviously have a much weaker pressure because this distance is so much longer. So distance has everything to do with how much pressure an electron is under. And this pressure, though, would probably be proportional to half of this pressure. You know, if you take this pressure and this pressure, added the two, and then divided by 2, that would be the pressure between these electrons. So that dictates this distance. So it's just pressure mediation, as some people would say. All right, so what did I want to say about what he just said? He said something just totally wrong. Oh yeah, so electrons will somehow just pop into this. They can't pop here. If this is full, they're not going to the ground state. Okay, so you can't just say an electron says, I'm going to the ground state. Well, it can't get to the ground state, so then it's stuck. And this is really the ground state, though. This is the place where it's not interested. Okay, it's far enough away from the proton that it just doesn't have much interest. So it'd be silly to say that its tendency is to jump into that pool when the pool has so little, there's nothing inviting it. So I'm just saying that, you know, they got it inverted. This is like the plus minus problem. They started with the wrong idea of where the pressure is, where the energy potential is. The potential is higher in the inside than on the outside.
The way an electron can give up energy is by emitting a photon. So after falling back down to the ground state, this electron would emit a 4 eV photon.
See, it can't really emit a whole photon, right? So you kind of understand, all it can do is move this way and move that way. So it add 1 or 2 bits, but you can't create a whole ray length of energy. It can't create the whole wave. All you can do is push it and it pushes back. So you can create one piece of the wave, and something else has to create the other pieces. Another atom has to create the other pieces.
Electrons don't have to just jump one energy level at a time, though. If the electron in our ground state were to absorb a 6 eV photon, the electron could jump all the way up to the 6 eV energy level. Now that the electron's at a higher energy level, it's gonna try to fall back down, but there's a couple ways it could fall back down.
Yeah, so the trick would be is that you can push this out to take this guy's place, right? I mean, I could hit this one, and this one moves fast towards this one, and this one just flies right out, right? I mean, so this one took this one's place, and then this one can move. But the point would be is that if this one left its position, that means this one, you know, theoretically the one over here, would go into that space, right? So if I took this one out, you can understand that this one would take its place. This one would fall into that space. It wants to, it is attracted to the proton. It wants to get closer. Well, if you just provided a hole for it to fall into, it's going to fall into the hole. So obviously, it won't be the same. It won't necessarily be the one you kicked out. It won't necessarily be the electron that fills the void. It's that, yes, one electron will leave and one electron will go in. So you'll have a balance in the sense that you'll have two movements that are going to be opposite each other on some theoretical angle line. Okay, so you'll have conservation of energy, and if you conserve the energy, then the whole atom can't have said something happened. So I guess that's another part of this that I think is a key ingredient to understanding what absorption is. And I would argue we know that transmission has to happen between the atoms. The atoms have to transmit what's going on. And so the key to absorption is that that's an atom where you hit it so right that you hit an electron in, the other electron comes, fills in the opposite, you know, fills that void so well that this whole atom doesn't do anything. You know, so you knocked an electron out to say the ground state here, and it's right there. And what happened was another electron popped in. That electron moved this electron over, and this one over, and this one just filled this outside position. So I mean, you did it so efficiently. All I'm saying is that you conserved all the energy. And so the atom itself didn't move. It didn't incur any change in its position overall, because all of the change happened inside the electron, because you hit the electron out exactly right to the surface, so it's just waiting to go back in. So essentially you're creating an ion, you're shooting an electron out, and the question is, do you have something to fill that void? And if you don't, it remains an ion, right? I mean, a piece can go in from the outside, but then you still have a hole here. So you still have an ion, and the ion means that it's going to move, the whole atom is going to move closer to the next atom, because it has an ion now, it's missing an electron. Or in a sense it has too many, because you've knocked it out too far. And so now there's too many electrons in the field, which means the two atoms are going to repel each other, because they're both going to be repulsive to that electron. So you're either creating pressure to move atoms towards each other or away from each other. But if you do it just right, that is, you hit the inside electron. Just draw that bigger. So there's an inside electron, proton here. You hit it just right, where you knock it right out to the outside. Now it stops. Okay, so it's just enough energy to fight the proton's attraction. So it pushes it right out to that limit, but it's right there where all the other outside electrons are. So now when they fill the void, that is, when they drop in to fill these holes, this one's right here to fill the last hole. So now the whole thing is balanced really quickly. So the atom never does anything. And if you get the atom to do nothing, then you've absorbed the photon. So the photon of that energy would be the absorption line, and the absorption line means the atom didn't do anything. You didn't create an ion for any long period of time. The ion only existed for a microsecond, where if you hit at some other frequency, you'll create evidence, you'll create bumps, you'll create jiggles in the atom, and then it'll jiggle the other atoms. So if you hit it just right, it just stays still. You hit it with a little too much energy or a little too little energy, then the atom itself will jiggle, and that'll jiggle the other atom, and that'll jiggle the other atom. That would be one way of explaining it. I think that's close to the well articulated truth. So that's what I said in there, is the concepts that when somebody finally says it exactly right, it'll sound kind of like that.
Down in this case, the electron could fall down to the ground state all in one shot, giving up a 6 eV photon in the process. But since the electron started at the 6 eV energy level, it could have also fallen first to the 4 eV energy level, emitting a 2 eV photon in the process. It's a 2 eV photon because the electron dropped 2 electron volts in energy. And now that the electron's at the 4 eV energy level, it'll...
So again, it's just moving. Every time you move an electron, you're essentially creating a photon, a piece of a photon, one of the little quanta. And the question is whether you move them all in the same way to send the quanta all in the same direction, so you could actually see them as a photon. But every time you change the position of an electron, you change what's reflecting off it. Just like, again, if I moved really quick away from the light at the speed of light, then none of the light can reflect off of me, and you'd see me disappear, right? So theoretically, if I moved really quick away from the light bulb, I would disappear. I'd be invisible. And then as soon as I stop, I'm going to be really visible, because now everything, okay, that didn't hit me before is now going to hit me. And so so I can't say more is going to hit you. So more only happens when you're moving towards. So if I move towards the light, then I get brighter. So if I could move the speed of light towards the light, I'd obviously become brighter, in the sense that I would blue shift. So the light would be brighter light, so to speak. I mean, more energy in the light, more photons, more little bits, more quanta. Yeah, so the going backwards one is the one it's easy to understand. So you can understand the disappearing thing and being twice as appearing by moving forward into the force. Yeah, so that's all that needs to. So again, the disappearing part is the part we know the photon has. It has that nothing bit. And the nothing bit is the tricky one to create, right? Nothing. So the only way you can create nothing is to move the same way the force is, and basically try to outrun it, and then you'll become invisible, and then you'll be able to create the nothing that's between the somethings and the frequency.
Fall back down to the ground state, emitting a 4 eV photon in the process. So electrons will sometimes drop multiple energy levels at a time, and sometimes they'll choose to take individual steps. But regardless, the energy of the photon is always equal to the difference in electron energy levels.
Right, so they're just saying the frequency. So when they say the energy of the photon, they're just saying the frequency at which you're potentially sending a change. You're making a change in the environment. But again, you can't make a change, you can't create the whole photon. So it has to, more than once it has to happen for you to create the length of photon, the ray length that you need. So it has to happen more than once, to more than one atom, to more than one electron, or you're not going to have a photon, because photons again are huge. So it's really a composite thing. You got to understand that this is many interactions being represented by that one photon. There's a whole bunch of other interactions that take place underlying that. So yes, theoretically one photon comes out of the group of atoms, but it only comes out of the group of atoms because a bunch of individual electrons made these individual changes to create the individual reflection that is the photon. It's all momentum. So if you push something one way, there can't be, you can't create more energy. You can only, undo something else that was done. So I'm just saying, if you're putting energy in this way, the theory is, that it's got to come out this way. I mean, that's where it's got to go. But because of the way the electrons are already storing energy in other momentums, they end up moving the energy from one this way to moving it that way, or moving it some other way. And there's always the same energy in, and it's just, you're just changing the timing of when it comes out. So again, the photon is just timing. So how to explain? Yeah, well, I won't bother trying. It's just that you're just adding, you have this coming, you have a bunch of this coming in, clumps of this stuff, and it seems like there is a huge likelihood that yes, it's going to go in here, get knocked, some of it's going to get busted out, some little pieces of it, but some of this will make it to this other side, and that's going to be your frequency. So all you need is some of these photons, the quanta, to survive to get to the other side for you to say, I see it. And the point is the atoms that don't move, that stay where they are, any photon that causes that to happen won't get here.
What if our electron's in the ground state?
It's like a head-on collision, right? I mean, you have the head-on collision, then you understand it's all even. But if one thing is way behind the other, then the collision's way over here. And, what's going to happen over here is going to be very different than if they had the collision right in the middle. So it's kind of like just saying that well, again, the point is that the atom doesn't move because the energy compensates. The movement of the electrons this way to fill the holes is the same energy it took to move the electron out of the hole, and so it's kind of circular, and therefore it doesn't create any imbalance in the atom.
And we send a 5 eV photon at it. If the electron were to absorb all of the energy of the 5 eV photon, it would now have 5 electron volts. But that's not an allowed energy level, so the electron can't absorb this photon, and the photon will pass straight through the atom. Keep in mind, the electron in the atom has to absorb all of the photon's energy.
Right, so that's, it can't happen that way. So it happens as there's a physical phenomenon that happens. Like I said, you put the right energy in, you'll keep the electron really close to the atom. If the electron stays close to the atom, then the atom can rebalance. If the electron goes far away from the atom, because it still has extra momentum, extra energy, then the atom is imbalanced, and it's going to have to imbalance the other atoms around it. So I think that's more a key to understanding it. If you kick the electron out at exactly the energy it takes to just leave it right here at the surface of the atom, leave it right on the surface, just enough energy to get to zero gravity, so to speak, just enough energy to get you beyond where gravity has a substantial influence, however you want to say that. So the thing is essentially standing still. There's not a much force acting on it, very little force acting on it. So you get the electron to where very little force is acting on it, then it hangs around, and then it can go back into the atom the way it's supposed to and rebalance the atom. But if you knock it out all the way, then that ion exists for too long, the atom moves, and if the atom moves, then the other atoms move.
Or none of it. It can't just absorb part of it. Alright, so now we can figure out every possible photon this atom could absorb. If the electron's in the ground state, it could absorb a 4 eV photon, or a 6 eV photon, or a 7 eV photon. If
those are all energy levels, so to speak. I mean, the amount of hitting or moving of an electron, you bang, bang, bang. And at those bang rates, you can move a specific, it depends on what electron you're hitting. So if you're hitting the little one, you'll bang it one place, move one place, and that's it. But the point is you're not hitting it hard enough to knock it out of the atom with any momentum. The key problem would be is in the last energy levels, you can hit an electron and it doesn't take much energy to move it out, so one quanta will kick that one out. So this is like constantly ionizing the atom. The atom is constantly being ionized in a sense, or changed in its electrical potential, because you keep fiddling with the electrons. And it's, of course there's some free electrons in this whole thing somewhere, and that's critical to most things that produce light with electricity. But anyway, well, let's not get into that.
the electron's at the second energy level, also called the first excited state, the electron could absorb a 2 eV photon or a 3 eV photon. And if the electron were at the third energy level, or the second excited state, the electron could absorb a 1 eV photon. Those are the only photons that this atom will be seen to absorb. 2.5 EV photons will pass straight through. 5 EV photons will pass straight through. 6.3 EV...
So none of them pass straight through, and the only thing that can pass through is either... To pass through, understand, light doesn't just let... glass doesn't let photons just pass through. Alright, so there is none of this just pass through stuff. We know there's a physical way that stuff gets transmitted. And so it's transmitted. It's not passed through. And so transmitted requires atoms to communicate with atoms. And so that's what transmitted means. So transmitted means you move the atom. Not transmitted means you didn't move the atom. And the trick is if you hit it with just the right energy, the atom doesn't move.
EV photons will pass straight through. What this means is that if you were to shine light that consisted of all possible wavelengths through a gas that was composed of our pretend atoms, all the wavelengths would not make it through. Some of the wavelengths would get absorbed, then scattered away in random directions. This would...
That's right, that's just the heat thing. So you're going to get lots of that's going to happen. When you're moving all these electrons around and jiggling all these atoms, that's obviously going to make heat. And some of it scatters in directions. Right, but transmission requires that it get consistently moved in one direction. That the atom itself jiggles in a direction. That's what transmission requires. And it's always slower than the speed of light, so it's always... You have to know that the force hits something. It didn't just travel through at the speed of light, okay? It hit stuff. It was transmitted. It didn't pass through. So I'm just saying it's really important to understand that nothing just passes through atoms. It has to be transmitted by the atom. Transmitted, and transmitted means transferred. The motion has to be transferred into motion of the atom. The atom has to move.
Manifest itself as dark lines in the spectrum.
I shouldn't say move, right? Because what I'm saying is that the atom has to change shape. This has to change shape.
missing wavelengths or missing energy levels that correspond to the energies of photons that our electron can absorb. This is like a fingerprint for an atom, and it's called that atom's absorption spectrum. If you were to ever see this progression of dark lines in these exact positions, you would know that the gas you were looking at was composed at least partly of our hypothetical atom.
Right, so they're just using hypothetical, and because this isn't perfect enough for them to use a real example. But yes, clearly, but this is understandable in the sense that, as I'm pointing out, at certain energy levels, that is, at certain kinds of photons going through, are more likely to hit electrons in such a way as it always creates a balance. That is, it always just hits the electron enough to, it's more likely to, let's just say. This is all about just probabilities. Again, if you narrow the polarization, there's more probability you're going to hit atoms in the same location. How else to put that? So that's more likely to create scatter, or it's more likely to create some other effect. But the specific lines are just basically saying that certain energies, when hitting an electron, are going to create nothing in terms of the movement of the atom. And not moving the atom is what those lines are representing. That's light that can't be transmitted because it didn't move the atom.
This also allows astronomers to determine what stuff in our universe is made out of, even though we can't get close enough to collect a sample. All we have to do is collect light from a distant star or quasar that shines through the stuff we're interested in, then just determine which wavelengths or energies got taken out. The details are a little messier than that, but this provides astronomers with maybe...
Yeah, it's a little nearly impossible in the sense that your light has to be, it's redshifted, and then the part of the problem, and it has the same elements in it that your cloud has in it, so it's already got absorption lines in it. So yeah, it's a little messy.
The most important tool at their disposal. Now, the absorption spectrum are all of the wavelengths or energies that an atom will absorb from light that passes through it. You could also ask about the emission spectrum. The emission spectrum are all of the wavelengths or...
So the emission spectrum would be back to where I was talking about the antenna part of light. So that's a lot easier to understand. That to be transmitted, it's just the idea of even the voltage idea. But the idea is the atom changes, and the change is transmitted through the atom, and the amount of time it takes to get from this atom to this atom to this atom to this atom is going to be decided by the structure of the electrons in the atom itself and how big the atom is. That's all more distance. So it's really telling you that this is the way the atoms are bound together, and that I can move an electron and it will transmit its momentum through these atoms at a specific speed, and that's what it's likely to transmit based on the atom size. So the distance the atoms have between each other, lots of things like that are going to dictate how likely it is you can create a certain amount of energy. So I can put a certain amount of momentum into a metal, and I can get X-rays to come out because the speed at which these atoms are connected, that is the depth of their connection. So you could almost argue that if you understood that they can share electrons on this outside ring, but they can also share electrons, on an inside ring. They can share electrons on, well, I didn't draw it right? Yeah, well, you just put one here. They can share an electron here, deeper, and that would make it even quicker to connect the atoms to each other, and even a stronger connection. So the stronger the bonds between the atoms, the faster you could understand the electricity, the motion, the momentum can travel through the atoms. The faster it can travel through, the higher the frequency, the outgoing, the sooner, piece of a photon, it's making the pieces quicker so they have a higher frequency. And if they're less bound, more loosely bound more on this outside level, then their frequency is going to be slower because it's going to take longer for the jiggle, so to speak, to get through the atoms, and so you're going to get a higher frequency. So metals are good at creating X-rays because they got a tight bond between the atoms, and so the momentum travels through the atoms much quicker, and therefore it can create the higher frequency emission.
energies that an atom will emit due to electrons falling down in energy levels. You could go through all the possibilities of an electron falling down again, but you'd realize you're going to get the exact same energies for the emission spectrum that you got for the absorption spectrum. So instead of letting light pass through a gas...
So they're not falling down, they're being pushed down, right? Because the external pressure is greater on the inside than the outside, blah, 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 blah.
Composed of your hypothetical atoms, let's say you made a container that had the gas of your hypothetical atoms and you ran an electric current through it, exciting those electrons to higher energy levels and letting them fall back down to lower energy levels. This is what happens in neon lights, or if you're in science class, is what happens in gas discharge tubes. So for the emission spectrum...
Right, they have a preferential, they have an atomic structure, and the atomic structure has a preferential frequency based on how fast momentum can be transferred between the atoms.
Instead of seeing the whole electromagnetic spectrum with a few lines missing, you're going to only see a handful of lines that correspond to the energies of those photons that atom will emit. Okay, I've got to be honest about something. If any physicists are watching this video, they're cringing because the energies that electrons will have in an atom are not positive. The energies an electron can have in an atom are actually all negative values.
Right, so why didn't you just start with that? You know, I mean, it's just so silly to start with 0, 4, 6, 7, and then say, no, we're changing the whole thing to exactly the opposite.
This is because the electron's bound to the atom. Anything that's bound to something else will have total energies that are negative. This is analogous to a ball stuck at the bottom of a ditch.
It's really not analogous to it in the sense that there's no negative energy. You know, there's just less, you know, more closer to zero.
The ball's not moving, it has no kinetic energy. And if we assume that ground...
I mean, ground is an obvious average. It's not, you know, ground isn't nothing between a negative and a positive. I mean, it's just a half positive.
Level is the h equals 0 position, then this ball is going to have a negative gravitational potential energy. Since this ball has a negative total energy, it's stuck and bound to the ditch. If someone could give this ball enough energy so that it would have positive total energy, the ball could leave the ditch. It would not be bound anymore. So to make our hypothetical atom a little more realistic...
So again, I don't know, you know, there's so many ways to draw it in terms of understanding the tension argument. You know, that it's just a ball on a string and you have to pull it a certain distance to break the strings, you know, or however you want to think about it, but it's just tension, and the tension isn't a zero state.
Let's subtract 10 EV from each energy level. This doesn't really change anything. In order for the electron to get from...
Well, it doesn't really change anything, except a 0 is a 10 and a 7 is a 2. But anyway, it's obviously a correction I would say is the right thing to do, is to make it understood that there's more potential in the inside and less potential on the outside. That the ground state is really the outside, not the inside.
From the negative 10 EV ground state to the negative 6 EV first excited state, it's still going to take a 4 EV photon. People do get confused with the negative signs though, so be careful. In order to find the energy of the photon that was absorbed or emitted, you always take the higher energy level and subtract from it the lower energy level. So in this case, we would take
Again, the energy is from an artificial ground, right? So again, they're just, you have to, you don't always need to do this positive negative thing for the purpose of just understanding how much force it takes. It takes the same force to climb 10 feet up a ladder, up a tree, that it takes to climb 10 feet out of a hole. So, I mean, the ground is arbitrary. You're just talking about the distance you're moving and what's resisting the distance. And obviously there's more resistance to motion close to the nucleus and less resistance to motion far away.
Negative 6 EV and subtract from it negative 10 EV, which tells us that it would take a 4 EV photon to bump an electron up to that energy level, and the electron would emit a 4 EV.
I mean, I don't know what the best analogy is to use, but maybe they should think about it almost in terms of mass, that the electron has more mass when it's close to the nucleus and less mass when it's further away. So the further away I take an electron and move it further away from a proton, the less mass it has.
Photon if it dropped back down from that level. Something else that's unrealistic about our hypothetical atom is that real atoms wouldn't just stop at -3 eV for the highest energy level. Real atoms have energy levels that get closer and closer together as you approach 0 eV. What happens when an electron gets more than...
Yeah, well, that implies, that it loses proportionality, and it doesn't lose proportionality. Obviously, the negatives are between the electrons. The energy between the electrons is always stable, and what you're doing is moving further and further away from the proton. So obviously, the amount that the electrons are pushing is much stronger than the amount the proton is pulling as you get further and further away. So yeah, the lines change, but they don't change the way, they don't just all of a sudden go down a hill. I don't know if it would calculate out to the inverse square law. So it's an R rule for the charges, but the point is that the R rule is stays constant for the electrons and is variable for the proton. The electrons always have to stay a distance from each other, but they're in a bigger orbit, so to speak. They're piled on a larger surface, so it's easy for them to be further apart. Now,
0 eV energy? Well, if an electron has more than 0 energy, that means it's got positive energy. And if it's got positive energy, it's not bound to the atom anymore. It'll be free to leave, it'll be gone, and we'll say that we've ionized.
Right, but the trick is where's it go? It hits another atom. So the energy from one atom hits another atom, and it's going to move that atom, and so on and so on and so on. So if you didn't have an efficient, if you didn't move your electrons from 10 to 0, or 3 to 0, or 5 to 0, and you left extra, you hit it with 5, you hit a 4 with a 5, and therefore it still has 1 left over. Well, that 1 is going to go to another atom. So, it doesn't go nowhere, and you need the other atoms to be creating your energy conservation. Their movement's going to create the other bits that create the new photons.
Is the atom by removing an electron. So for example, say the electron started at the -4 eV energy level, and it absorbed a 7 eV photon. That electron would have a total energy of +3 eV, and so it would be gone from the atom.
Alright, so the thing I really don't like about that is they're combining by giving them the same energy. Like I said, the photons don't have electron volts. It's a frequency, and it's just, I don't think there's any real point in converting frequency into momentum or velocity. The two things aren't the same thing. So that's one part of this that just kind of makes a mess. Because they're just saying, well, what's capable of doing it? Well, it's only capable of doing it, again, if it can hit it. So, we have an electron in tension, and we're saying it's a 5 eV. So we're just saying that's how strong the tension it's in. So if we hit it with a 6, all right, then we're going to knock it free. We'll break these bonds. And the key is there's something else to fill that void. So, you still have this one extra that's going to be left over. And that's going to go into another atom, another atom in the same way as your 6 went in. So now your 1 is going to go into another atom and jiggle something. So I don't, it's not very constructive to use frequency, because it's different than velocity. They're not the same thing. They'll be converted. Whatever, I just don't know. There's ways of saying it, right? But it's a number of things you're hitting. It's the number of bullets that are going to decide how fast that electron's going. And it's quantized. It can only go like 30 miles an hour, 60 miles an hour, 90 miles an hour. It has to go a speed that's proportional to the tension that you're knocking it out of. It's either 1 or 2 or 3 units of momentum, more or less. I mean, I guess units of momentum would be a better way to do it. So, well, anyway, I'll think on that. So anyway, this whole subject needs more work and all that stuff. I just wanted to lay some groundwork and just make a comparison, just showing that from the previous videos on light and the two-slit experiment that you can migrate the theory to these other things and explain with this understanding that photons are not just wiggly lines, that photons don't individually act on a single electron. The whole photon doesn't act on one electron, that this is a behavior that comes out of composites, out of, you know, more than one atom creates the photon, more than one atom receives the photon. It's not just something one electron does. All right, that's the important point. Well, it's one of the important points. Yeah, one of them. Okay, so till the next time and such.